So this video is going to go over just what the equilibrium constant K represents. Now we're going to calculate it in other videos, but we're going to go over what it represents in this one. So it's a dynamic state where the forward and the reverse rates of a reaction are equal to one another. So that means that the traditional arrow that we would use for a reaction, like A going to B, actually is split up into two arrows, where there's a forward reaction and then there's a reverse reaction. And what that means is that we would have to look at a reaction where A goes to B and a reaction where B goes to A, and the rate of those two things is equal. And that is a dynamic state. And what that really means is that if you can envision a plot, let's draw a little plot here. And here's time in our plot, and then we have concentration of A, concentration of B here. So I'm going to show A. So at the very start of our reaction, we've got nothing but A, so it's got a relatively high concentration. And over time, its concentration is going to decrease. Okay? And over here, I've got B in red, and at the start of our reaction, we've got absolutely no B, so its concentration is 0, but over time, it will start to increase and level off. And where both of these no longer have changes in their rate of reaction, that is our equilibrium state, when these lines end up balancing off. So from this point forward, this is equilibrium. Okay, so that's sort of what equilibrium represents. We represent that with a constant K, which is the ratio of the concentration of all the things we have in a reaction at a certain time. So our equilibrium constant K is the ratio of our products, the way a reaction is written, to our reactants. Okay, so it's the concentration of C times the concentration of D over the concentration of A and the concentration of B. But the way it's represented is that these coefficients here, this lowercase c, lowercase d, become exponents here. Okay, so it's c raised to the little c, d raised to the little d, a raised to the little a, b raised to the little b. Okay, so for a reaction like this one here, H2 and Br goes to make H2HBr, the way we would write the K equilibrium constant for that would be the concentration of HBr squared over the concentration of H2 and the concentration of Br2. And these constants actually have numerical values, and we're going to work with those quite a bit in this class. So 1.9 times 10 to the 19th, and this is at a certain temperature, so at 25 degrees Celsius. We're not going to pay too much attention to that just yet. It'll be important later. But this is a huge value, and what that means is that our products are favored at equilibrium. That means that in order for us to have such a high value of K, so if K is much greater than 1, that means that we have a lot of products and not a lot of reactants at equilibrium. So products are favored. In this reaction here, nitrogen plus oxygen goes to NO. Again, we're going to write it almost the exact same way, but the constant here, the reaction constant, is very different. 4.1 times 10 to the minus 31 at 25 degrees Celsius. The only way we get to have a reaction quotient, a reaction constant at such a low value means that our numerator is very small and our denominator is very big. So this means that our reactants are favored. There is a reaction that's taking place here. However, that reaction doesn't go very far in this direction. So in this reaction, things spend most of their time being reactants, and in this reaction, things spend most of their time being products. Okay, so that's what the value of K represents. Big K, lots of products. Little k, lots of reactants. Hope that helps.